take a look at a couple diagram problems from the textbook. This one says to draw the impulse momentum diagram. How might you know that'd be a good approach? Is because it's asking about velocity at a certain time. We see up in the diagram we've got a t equals 0 all the way to t equals 3, so that's going to be t1. That's going to be d2. So our impulse momentum looks like mv at time 1 plus the integral across the time, which is going to be the forces integrated, and that's going to be then equal to the mass times the velocity at 2. So we are going to draw a picture of the collar, and so time 1, and there's going to be our impulse, and then at time 2. So initially we're told that it's at rest, so I'm going to draw nothing there. I end up then working across the impulse, right? Applied to it is a force P, which again is a function of time. So again, I'm going to need to integrate from T1, which is 0, to T2, which is 3. Going down, I would have the weight times delta T, right? The weight is a constant. Delta T is equal to 3 seconds. Right, I need to include weight because delta T is a substantial amount of time. You see that you've got a force of 10 and we've got a weight of 4, so that's going to be significant to use. And what we'll be able to do is come up with the mass times V2, which if we look up at the picture, right, it would be moving up. So I can go ahead and draw the velocity up. And now I've got, again, to analyze that, I need to do one last thing. I need to put my coordinate system on, so I can call that x and y. And then to analyze this thing, I'm going to sum linear momentum in the y direction. I can go ahead and call 0 up, and that'll end up with an equation. So what I need then, when I evaluate that term right there, I'm going to end up needing all the area underneath there. Here's our next problem. If you want to go ahead and pause it and read it, feel free. So what you'll find is this problem statement deals with that suitcase right there. So that suitcase falls down when the other luggage is removed, and again, it is free to slide. So that's one thing we're going to want to keep track of. And so what you're asked in part A is the velocity of A, the bag, as it rolls on the carrier. So let's go ahead and take a look at the impact when that piece of luggage falls down on the cart. So let's go ahead and draw the cart with the suitcase right there at an angle. And we then have the cart with that suitcase sitting down. That's our impact. And then we've got after at some other time. So after impact, that suitcase is then moving. So let's go take a look at what we have here. We've got no velocity, right? Velocity equals 0 at the start. Thing is going to slam down, and so we've got mg times delta t. A little more interesting, we'd end up with the integral of the normal force from T1 to T2. Over here again we'd have the integral of the normal force, a different one, from T1 to T2. And we'd also have the mass times the gravity of the cart times delta T. And I'm going to do it in red that I like to do. We would have a big impact force right there. So that's that big red arrow. I'm going to call that F delta T, and equal and opposite because it's going to be internal to the system. And then afterwards we have the suitcase, which we will call A. having a velocity, happens to be on the cart, but again, we're going to deal with the velocity of the suitcase itself. We've also got the mass of the carrier, which we will call B, times the velocity of B. And so if we look at our impulse momentum diagram, we've got one more thing to add, and it would be a coordinate system XY. And so our way to attack this is we are going to sum linear momentum in the X direction, and we would see we have nothing, right? We have nothing here because all the static loads are in the Y direction. And over here we would have two terms. And as we look back up in the problem statement, we would see that the velocity of B was told to us. So we'd be able to solve for the velocity of A. Part B, it says the velocity of the carrier after the suitcase hits the right side of the carrier without bouncing. So that means it's a plastic collision, so they are going to just stick together. So we need to do another impulse momentum diagram, which is going to represent the cart and the suitcase, which again is rolling freely right before impact. Get it right here. This is going to be right at impact. Those edges are touching each other. And then afterwards, they are moving together. So we can go ahead and talk about initially. We have got mass of A times the velocity of A. Right, that was solved from above. Here we've got the mass of B times the velocity of B. Across the impulse, we've got all these forces in the vertical direction. We've got weights, we've got normal forces, and we've got our impulsive force. It's going to act over a very short period of time right there. So I'm just going to represent equal and opposite. Again, it is internal to the system. And then afterwards, these two are working together. So I would have the mass of A plus the mass of B times V prime, or V after, right? After they have hit and stuck to each other. So we've got one last thing just to put our coordinate system on. We'd have an X and a Y. And the way we would attack this is some linear momentum in the X direction. And our unknown would be the velocity after. As it sits right now, we know the velocity of A from above. We know the velocity of B because we were told that in the problem statement. Here's another impulse momentum picture. It's going to ask you for that diagram because we're going to want to know the velocity at a certain time. This one happens to be immediately after the cord becomes taut, which supplies an impulsive load to our system. So here's our system. We're going to draw this thing right before it becomes taut. So there's A. I'm going to draw it just up here. It's got just a little wave to it. Right, there would be B. We're going to then have this thing go taut. And then afterwards, we've got masses times velocity after. So let's go ahead and take a look at what we know here on the front side. I would know that, as we're told, each of mass m, so this is going to be mass. We're given a initial velocity up. Right? Again, this is right before the impulsive load is applied, right? This thing becomes taut. So at that time, right, as it becomes taut, we've got F times delta t. Right, we've got that impulsive F times delta t equal and opposite. And then afterwards, we've got velocities that we have to deal with. So if something, block A right there, if block A is sitting and then all of a sudden a force is applied to it in a certain direction, obviously this is along the cord direction, that would mean that its velocity would be going in the direction of the force. So this would be mv prime A. And so before we get a little further, I'm going to go ahead and put a coordinate system on. This would be the x direction. That would be the y direction. So this would be mv prime A in the x direction. Up at B, I actually don't know the direction. I'm going to draw one right here because I'm going to have m times the velocity prime B in the x direction. And I'm also going to draw one perpendicular to it, mv prime B in the y direction. Again, that's just a way of saying I don't know what the velocity is. And so as we kind of look at our unknowns here, I've got an unknown velocity x, I've got an unknown velocity B in the y direction, and also a third one right there. And so we have one more piece of information to help us, because right now we have 3 equations and only 2 unknowns. And that would come from the fact that it is an inextensible inelastic chord. So that would tell us kinematically that Vax after would have to be the same as VB prime in the x direction. We're going to have the same velocities, right, along the length of the chord, because it is not going to extend